Hi everybody, I am Siddharth Katageri from KLE Technological University and I'm glad to present our work ABD-Net, Attention-Based Decomposition Network for 3D Point Cloud Decomposition. This is a joint work with Shashidhar Kudari, Gunari, Ramesh Tabib and Mudenagudi. Supervising a machine to derive relevant structures and high-level relational understanding of the 3D world is a challenging task. However, representing a 3D object with a set of basic geometric paths simplifies its geometric shape, which is helpful for better shape analysis. Tasks such as point cloud classification would really improve by knowing the underlying inherent structure of the 3D object. Along with it, point cloud decomposition would also greatly assist point cloud synthesis tasks like 3D super resolution and 3D hole filling, as an interpolation function can be learned based on the detected shapes. Previous work on point cloud decomposition cover both classical and deep learning approaches. One type of classical approach is using ransack, which tries to decompose a point cloud by considering it as a problem of basic shape fitting. However, it is non-scalable as it requires manual parameter tuning, which is labor intensive. Another promising work extracts handcrafted features, them being metric tensors and Christopher symbols, followed by a SVM classifier. The performance of this model may be constrained on the representation power of the handcrafted features. Recent deep learning approaches propose basic shape fitting on point clouds, which is a complex task, making it computationally costly. We tackle the problem of missing superficial information by representing the inherent geometry of 3D point cloud using four basic shapes, namely plane, sphere, cone, and cylinder. We perform decomposition by assigning per point labels from one of the four shapes, making it a simpler problem than basic shape fitting. In order to get better point cloud decomposition, it should be based on both local and global geometry. The local geometry accounts for fine-grained details and the global geometry considers the overall shape of the point cloud, resulting in better feature extraction. We choose to demonstrate the effectiveness of decomposition on 3D point cloud classification task. We aim to use the learned decomposition features for classification, along with the point coordinates. In this paper, we propose attention-based 3D point cloud decomposition network. The proposed local proximity encapsulator captures the local geometric variations along with spatial encoding around each point from the input point sets. The encapsulated features are further passed to the proposed attention feature encoder to learn basic shapes in the point cloud. Attention feature encoder models geometric relationship between the neighborhoods of all the points, resulting in capturing global point cloud information. Local proximity encapsulator extracts representation of each point considering features of its neighborhood, capturing fine-grained details of local point sets. LP first defines patches on point clouds and then processes each patch individually, extracting local geometric information along with spatial encoding, thus incorporating local attention. Specifically, it first transforms the points to higher dimensional space. Then, to account for local geometric information, the point cloud is divided into subsets of neighboring points using k-nearest neighbor. Each patch is further processed with a set of shared MLPs. Finally, dealing with the unordered nature of point clouds, it is passed through an average pooling function to aggregate the features of the neighborhood. Attention feature encoder models geometric relationship between the local neighborhood of all the points, thus incorporating global attention. The attention is based on basic shapes present in point clouds. As our attention mechanism, we use scaled dot product where KQV are abstraction of the input in the transformed space. Here, query matrix represents the target input point which is to be processed. Key matrix represents key features of the input, and the value matrix is a representation of the input. The idea is, whenever we are required to calculate the attention of a target point with respect to the input points, we should use the query of the target and the key of the input to calculate a score or attention weights. The score is then multiplied with the value matrix to keep intact the values of the points we want to focus on and diminish irrelevant points. These features are refined by a set of fully connected layers to output global attention features. The following process is performed parallelly across multiple heads, dealing with different representational subspaces. The attention features can be used as geometric features for various 3D analysis tasks. To show the effectiveness of the attention features learned by a trained ABD-Net, we train a 3D classifier using its attention features. Note that ABD-Net is trained on ANSI dataset and the 3D classifier is trained on ModelNet 40 dataset. The architecture we use for 3D classifier is very simple, which includes 4 shared MLP layers followed by a max pooling and 1 fully connected layer. Similar to transfer learning, the weights of pre-trained ABD-Net is freezed while training the 3D classifier. The input of 3D classifier are point coordinates of the input point cloud and the corresponding attention features acquired by pre-trained ABD-Net. Here are some visualization of the results of basic shape decomposition using our proposed architecture on ANSI mechanical component dataset. Our proposed model achieves an overall accuracy of 99.3% on ANSI test set. Here, we show basic shape decomposition using our proposed model on ModelNet 40 dataset. Recall, ABD-Net is trained only on ANSI dataset, yet it performs exceedingly well on this unseen data. Also, the object shapes are totally diverse between the two datasets, showing generalizability of decomposition. We show quantitative comparisons with the state-of-the-art classification techniques. Our proposed classifier with ABD-Net achieves improved results over many methods. State-of-the-art point transformer-based classifiers have quite high number of trainable parameters. Our method achieves 92.8% of overall classification accuracy on ModelNet dataset, with 3 times less parameters than the other methods. To analyze the decomposition performance of our model, we perform a robustness test with varying point densities. Even though our model is only trained on point clouds with 1024 points, it maintains good performance for all point densities. Overall, the model exhibits its density invariant property. Further, we perform robustness test with point perturbations. Even when the point cloud is distorted with severe noise with a standard deviation of 0.05, our model achieves promising accuracy of 91%. These results indicate that our proposed ABD-Net is robust to point distortions, thus exhibiting its noise invariant property. To get a better understanding of the attention weights, we perform attention visualization. We extract the top 100 points which the model tends to give maximum attention while encoding a query point. We observe that each head of AFE models some kind of importance relationship. To analyze the classification performance with and without ABD-Net, we perform robustness test with varying point densities and noise variations. In both the cases, the classifier with ABD-Net achieves excellent performance by maintaining classification confidence above 95% in each setting. This shows that the feature extracted by ABD-Net are well suited for 3D classification tasks. The code of this work is available at the given link. Thank you for your time and attention.